Section 6.6, talking about graphing basic trigonometric functions. We're going to actually look at all 6 of the trig functions. And then in 6.7, where we talk about modeling or doing applications of the trig functions, we will focus on the sine and the cosine graph and how we can transform them. All right, so we have to go back and review that the sine and the cosine curve are modeled from what we refer to as our unit circle with a radius of 1, and what we were modeling was 2 things. We were modeling for a cosine value. We were modeling the x values of a point that move around the unit circle. So how far away from the origin in the x direction is what the cosine curve will model. And then in the sine curve, we are modeling that y values of that same point as we move around the curve. So now we're talking about the y direction. How far away from the origin are we in the y direction with sine? And there are basically 5 main points that we look at for sines and cosine curves. And then there are some intermediate points that help us kind of detail the curve. But let's talk about the main points that we would consider for sine and cosine curve. And these 2 graphs, tables that we're going to generate here, we'll refer to as our parent functions. This is without any transformation occurring to the graph. If I were to put in the following values for theta, now this could also be x, so I'm doing this in degrees, but we can also be doing this in radians. So I'm going to put the following theta values in: 0, 90, 180, 270, and 360. Again, these are the same thing as 0, pi over 2, pi, 3 pi over 2, and 2 pi radians. What would I get if I stuck these values in for a cosine function? Well, if you were to just pull out a calculator, put it in degree mode, put the sine and cosine of 0 in here, you're going to find that you're going to get 1. And then if you put the cosine of 90, you're going to get 0. And then the cosine of 180 would be negative 1. Cosine of 270 would be 0. Cosine of 360 would be a positive 1. And then I could take those 5 points and I can use those to graph my function. Now, I refer to quartering when I talk about graphing sines and cosines. And what's unique about a cosine function, we'll see in just a second, is where it starts. And a cosine function will start either at what is its maximum value or its minimum value, depending on if it's a negative cosine theta or a positive cosine theta. And then it'll go through its quarter points. So this is the first quarter, the second quarter, the third quarter, and the fourth quarter. And those are the points that I use to generate my graphs, even when I'm transforming them. So when we start to introduce vertical and horizontal shrinks or stretches, or we talk about left or right translation, up or down translations, I can still use these values to help me draw my graph. All right, what about for a sine? So we use the same theta values. Again, working in degrees, but this could be radians. What happens when you put a sine of 0 in your calculator? You're going to get 0. A sine of 90 is a 1. A sine of 180 is back to a 0. Sine of 270 is negative 1, and sine of 360 is back to a 0. And once again, same concept. I consider that as my start point, which, unlike the cosine curve, actually starts on what is known as its axis. We'll talk about this in some detail with the next section. So a sine curve begins on its axis, and a cosine curve either begins at its max or its min value, depending on if it's, again, a negative cosine versus a positive cosine. All right, so these are just some general things to kind of keep in mind here as we're talking about graphing sines and cosines. And then tangents and cosecants and secants and cotangents are a little different. Same idea in terms of creating a table of values. But with those functions, we typically have to use a little more in the way of theta values, not just these 5. All right, so here's what we would get for our sine and cosine function. I'm going to show you a little visual here of what's going on. with sine and cosine curves and how they are being created. So you see these two curves kind of working here independently. The one on top is the sine curve, and I talked about how the sine curve measures the y value. So you see on the left-hand side the unit circle, and the red line there, the vertical line showing you the y values of points as you move around the unit circle, and the resulting curve that you get is the sine curve on the right-hand side. The cosine curve, the one in green, talked about cosine measuring x values from the origin. So you can see on the left-hand side the unit circle as the point spins around. You can see what the x values there are, and the resulting curve on the right. So these are our sine and our cosine curves. Here's what they are generically, and this is the pattern you're going to need to know. Now, I've graphed these guys over an interval of negative 360 to positive 360, or negative 2 pi to 2 pi. And you'll often see that written like this. If it's in theta, it's going to be written as an interval like that. If it's in radians, typically x. So again, that just tells me where I'm starting and where I'm stopping. So we're seeing two patterns of these curves. And these patterns, so let's talk about what a pattern is. A pattern is the repetitive part of these functions. These are called periodic functions because they have a repeated pattern. And that pattern that repeats is known as a cycle. The number of degrees or radians, or in some cases time that it takes. So from here to here is known as period. In this case, we have a cosine curve that has a period of 2 pi or 360 degrees. That's how long it takes to go from some start point at a maximum to go through the entire pattern and get back to that maximum. So there's the period of a cosine function. Starts at the upper value and then goes down to a minimum value. And it's going through, in this case, the x-axis happens to be the graph's axis. We'll talk again about axis in more detail in section 7. What about a sine curve? So we check sine curve and we find its pattern. So we're going to say, let's start there. And let's go through one of its cycles. And we get back to the same spot for which I would begin repeating that cycle. So a sine curve also has a period of 360 degrees. And you have to just be careful when you're talking about going from a point back to its same spot. You can get stuck if you look at those 2 points. You're saying, I'm starting at an axis, I'm going through some degree value, and I'm getting back to that axis point. But you have to be careful because this does not represent the full pattern of the sine curve. That's just the upper portion. You still have the lower portion to consider before you actually get back to the starting point again. So just be careful with sine curves in terms of looking at their cycle or their period. All right, now we get into the unique ones with tangent and the reciprocal functions. So we're just introducing these, and yeah, you should have a good idea of what they look like, but we won't be using them in terms of a modeling situation. So unique to tangent and reciprocal functions is these functions can have places where my graph is undefined, where I'm dividing by a 0 for my ratios. And when I divide by a 0, as in the case of a tangent, y over x, if that x happens to be a 0, I get an undefined value, and an undefined value results in vertical asymptotes. So we're going to have vertical asymptotes for our tangent curves and then the reciprocal functions. So this tangent has a relationship of y divided by x. Everywhere where x equals 0, I'm going to have undefined values. So that's what we've got here. So where does x equal 0 for a tangent? Well, the tangent of 90 degrees is equal to 0. So we see they've graphed them in gray. See these vertical lines here at every pi over 2 plus pi. Well, plus n times pi, I should say. So pi over 2 plus n times pi, where n would represent an integer number, would take me back to where I have asymptotes. So what's unique about the tangent curve, besides the fact that it has asymptotes, is it has, you'll notice, a period of only pi, or 180 degrees. Because that pattern that I see, this green, sideways, vertical S-looking pattern, repeats every pi units. Now, how do they get these points? Well, if we were to put a table together, all right, so we have these periods of pi, and we have these curves. And if I were to put a t-table together, just like we did for sine and cosine, I would end up having to use, instead of just 0 and 90 and 180 and 270 and 360, I'd actually have to use a couple more points. So let's see what happens. We're going to take a look at what's going on in this area right here. How do we generate this curve? Well, let's look on the right-hand side of 0. Let's say we introduce the tangent of 45 degrees, which we know is 1. So 45 degrees is halfway between 0 and pi over 2. And these are increments of 2 on this graph. So we're right about there. So 45 degrees is producing a y value of 1. And what about 30 degrees? 30 degrees would produce a y value of 1 over the root 3. So you're talking somewhere around there. 60 degrees, just root 3. And that's going to be somewhere around there. So if I were to take all those points and plot them and connect them, I get this curve that results. All right, just kind of hopping through, plugging values into the table, and then again, that's how we get this curve. But I'm just looking at a t-table and using my main points, but I'm also considering some intermediate values. And I can keep going in this pattern. And that's how I'm getting these answers. So 1 over root 3, 1, root 3, undefined, and then again I can keep going. So there's our tangent curve. Unique one. What about, and then feel free to go back and check out this website here, this link here that shows how the tangent is generated. Again, it's because of the relationship of y over x. We are creating this curve here. Let's go take a look at the other functions real quick. The secant and the cosecant function. We haven't, back up real fast. The cotangent graph, it's not really, I don't have a separate drawing for that, but let's just real quickly take a look at what would you get if you had this x over y relationship. Well now, because I have y in the denominator, I can't have wherever there are y equals zeros, so y equals zeros at 0 and at 180. That's the place where my cotangent is going to be undefined. So my cotangent would have its vertical asymptotes at every 0, pi, 2 pi, and going backwards, negative pi. And its curve would just, if I were to plug in the x and y values into my table, it actually kind of goes the opposite direction of our tangent curve. So it would do something like this. That would be what the cotangent curve would look like. And again, if you go onto that website, you can check out how it's created. So it is www.intmath.com. And check out that link right there. You can check out the cotangent curve. Secant and cosecant. For the secant graph, we know that's a relationship of 1 over cosine. So what I'm going to do here to kind of get a relationship between the two is graph the cosine curve. Cosine curve would start at the max, and then at 90 degrees it goes to 0, and then at pi it goes to -1, and then at 3 pi over 2 back to 0, and at 2 pi we go back to 1. So it would look like this, and then I would repeat that pattern. And we get something like that. That's the cosine curve. And we notice that there are a couple places where the cosine curve and the secant curve share the same values, and that's because there are places where cosine equals 1 and -1, and the reciprocal of 1 and -1 is still 1 and -1. So why then these parabolic-looking shapes here? Again, if I were to put it into my table, I encourage you to go do this. 0s, 30s, 45. And with this, it probably would be better to even consider values of theta that are right next to these asymptotes. Get closer and closer and closer and closer to those values, and you're going to see how these curves rise up and get approaching or get next to the asymptote, or sometimes they'll go negatively approach the asymptote. So again, I would just say, check out your values, see what you're going to find in here. At 0 degrees, we said we were undefined. 30 degrees, the cosine of 30 degrees is a √3 over 2, so a secant of 30 degrees is a 2 over √3. And cosine of 45 is a 1 over √2, so a √2 over 1 would be the secant. And cosine of 60 is 1/2, so cosine of a 60, secant of a 60 would be 2. And again, I would continue that pattern to see what that points are doing. And I would get the resulting shape. So the asymptotes. Where do the asymptotes occur for a secant curve? At every pi over 2 plus n pi. That's just the same thing as it was for a tangent. And then we're back now to seeing the repeated pattern over a 2 pi or 360-degree cycle. What the repeated pattern is it's these green. So there's 1, 2. There's the repeated pattern, and then I would start that over again. So don't think of each of these U's, one of those opening up U's, as a pattern. If that was the case, I would see another one right there, but I don't see that. That's not the pattern that is repeating. All right, so that is our secant graph. Our cosecant function looks very similar, but it will have different asymptotes. So now cosecant, which is the reciprocal of a sine, and it is the r over y value. So wherever my y is equal to 0 is where I'll have my vertical asymptotes, and y equals 0 at 0, and 360 again. So we see asymptotes at pi and 2 pi, where in the secant curve we saw them at pi over 2 and 3 pi over 2. I'm going to draw the sine curve in, just so we can see the relationship. So at 0, 0, my start point. At pi over 2, we're at 1. At pi, we're back to 0. 3 pi over 2, we're at -1. And 2 pi back to 0. So here is the sine curve. And then we would, of course, continue that through the cycle here, through the pattern. And then again, just like in the cosecant or the secant curve, we have reciprocal relationships of 1 and -1, so we share some common points between the sine curve and its reciprocal function. And plugging in values, I get these U shapes, and they're just shifted from the cosecant curve. So asymptotes at every pi. Period, once again, back to 2 pi. So the only graphs that don't have a 2 pi period are our cotangent and then the tangent functions. All right, so I just need you to be aware of what these look like and how you can sketch them real quickly. Again, we'll emphasize sine and cosine functions, though, with the next section. All right, let's answer a few questions with regards to these. What are the periods of all 6 of our functions? Well, we said for all of them with the exception of cotangent and tangent, we'd say that sine, cosine, cosecant, and secant next slide. But why don't you check them out, and we'll pause for a second for you to go explore on your own and see if you can come up with some values. But how far does the graph of each function deviate from the x-axis? Meaning, basically, we're looking at what are the max and min values. So you can go check that one out for each of the functions. What are the x-intercepts of the graph? Again, the interval is saying between negative 2 pi and 2 pi. Number 4, which functions are undefined? So we're again thinking, when I see the word undefined, I'm thinking about vertical asymptotes. Where are the vertical asymptotes? For which graphs have them? At x equals 0. All right, take a pause, and then see how we did. Okay, so here are our answers for the 2, 3, and 4. How far does the graph deviate from the x-axis? For sines and cosines, it goes between -1 and 1. For tangents and cotangents, our y values are all reals. And for secants and cosecants, it has a -infinity to -1 union with a 1 to infinity values for y. The x-intercepts for the graphs between -2 pi and 2 pi. Cosine thetas would be, and these are all plus or minus values, plus or minus, plus or minus. So plus or minus pi over 2, plus or minus 3 pi over 2. And then for sines, again, plus or minus values. 2 pi, pi, 0. Same thing with tangent, cotangents, plus or minus pi over 2, plus or minus 3 pi over 2. Secants and cosecants, no x-intercepts. And then what are the functions that are undefined at x equals 0 or have vertical asymptotes at x equals 0? Cotangent theta and cosecant theta. Here's our next two. Try those. And for 5 and 6, which functions are undefined at x equals pi over 2? Secant and tangent are. And at what points between the -2 pi to 2 pi interval do the vertical asymptotes, if they exist, cross the x-axis? And they do not exist. Vertical asymptotes do not exist for sine and cosine, but for tangents, they occur at pi plus or minus pi over 2, 3, plus or minus 3 pi over 2s. Cotangents at 0 and plus or minus 2 pi and plus or minus pi. That would be the same for a cosecant. And then the secant at plus or minus pi over 2, plus or minus 3 pi over 2. There we go.